Hello everyone, I'm Teacher Xie, and the course we are doing today is the feedback control application. For last week's class, we used ultrasonic or infrared sensors to control the on and off light of an LED. What we are going to do in the next course is what we call closed loop control. This closed loop control has a feedback. What does this feedback refers to? It refers to the data measured by the sensor, then sent back to the controller to make adjustment in the power output. Taking the following class as an example, we are going to make a constant speed motor rotation system. At the beginning of the whole system, we will set a target speed. For example, we want 200 RPM, and this data will be sent to the controller, informing it that the motor will perform at such speed. The controller will estimate the power that shall be given to the output, which in this case is the motor. So the controller will give out a power output. When this motor is rotating, I expect the speed to be 200 RPM. But in reality, it's not like that. Its speed may be a little higher. What should we do when it is higher? The function of the sensor is to measure the actual speed. If the actual speed measured is higher than 200 RPM, then my sensor will send this data back to the controller. What will the controller do? It will reduce this power output. On the contrary, if the speed happens to get slower, the sensor will sense this situation where the speed is slow, and it will send this data back to the controller and inform that the motor is too slow, that the power needs to be adjusted up. This kind of control system is called feedback. What does feedback mean? It is a process of the output's physical quantity being collected by the sensor and then sent back to the controller to perform power adjustments. What we are going to perform in the following class is the control of the motor's rotating speed, so we are going to need a circuit board. This circuit board is called the motor control shield. We already have it during our last class, but at that time we used it as an extension for pin connection. For the following class, we want to give this motor control shield the responsibility of driving the motor. Why do we need this motor control shield? Because the current output of the node MCU is very small. It cannot drive a motor directly. What should we do? With the help of this motor control shield, we want to use the node MCU's small current to drive the motor control shield so that we can control the motor. Otherwise, if we use the node MCU to drive the motor directly, the node MCU will probably burn out. In the following class, we will first introduce this motor control shield. First, let's look at this. There is a switch at this part of the motor control shield which will determine whether the motor control shield's power supply should be on or off. Second, this motor control shield usually has a dual power supply. Why do we need a dual power supply? The reason is this. In here, there is a VIN and VM. VM refers to the motor's power supply. VIN refers to the control system's power supply. Normally, for driver control systems, we usually separate the driving power and the control system power. Because when the driving power is used, it sometimes may require a large current. When it uses a large current, it may drain all the power from the battery. What will this cause? There will be insufficient power for the control system. What will happen with insufficient current? The control board will burn out, so we hope for a dual power supply. However, for our following class, in order to achieve a smaller vehicle size, while also lowering costs, so we will be using a single power supply. The setting of this motor control shield can also accept single power supply. This node MCU can also accept single power supply. If you assume that you will use a single power supply, we can add a short circuit ring at VM and VIN, which is also called a jumper. By adding this, even if VIN and VM short circuit, the supply of power to both of them can be done simultaneously. This way we can use a single power supply. Next is these connectors. Two voltages can be measured within this board. The first one is 3.3 volts. Who is supplying this 3.3 volts? When VIN comes in, the node MCU itself has a voltage regulator. it will regulate the power supply's VIN to 3.3 volts. This whole row's voltage is 3.3 volts. The second one is the unregulated voltage. When VIN comes in, it will go directly to the back to be used. That's why it's called VIN. It hasn't been regulated. There's a total of 2 VIN connectors from which you can directly get 8.4 volts to 7.4 volts because when two 18650s are connected in series, it is 8.4 volts when fully charged. At its lowest, it cannot be less than 7.4 volts because over-discharging and overcharging are not good for the battery. Next, I would also like to remind you that the analog output is quite special. For our analog input, we need to use AD and not A0. Although A0 can be directly connected to this pin, but the analog output voltage that it can measure is lower. Only 1 volt. So we set up voltage divider resistor to increase it to the analog input that we can measure, which is 3.3 volts. So if you need to do analog input, remember to connect it to the AD pin. This is the introduction to the motor control shield. I would also like to remind you of one last thing. When operating this power switch, based on my practical and operational experience, this board switch can break easily. I suggest that you try not to use it. Use the switch in our battery box instead. The switch on the battery box has an on and off display so that you know if it's on or off. But this motor control shield's power supply uses a push switch, which has 2 types. One is pressed down to activate and the other one is pressed up to activate, and it is difficult to distinguish. Therefore, I suggest that when you are working with the board, do not use the power switch and use the motor power supply switch to determine whether the motor control shield is powered. Next, let's look at its working specs, which is another important part. The motor control shield's job is to replace the node MCU in the supplying of large currents, so the current it can provide is much greater than the node MCU's the working current. However, it still has a limit. For this L293 motor control shield, its working current can only reach up to 1.2 ampere. If exceeded, it may cause the burnout of the L293 motor control shield. So you need to be careful about this. Second, this motor control shield has 2 types of power supply input. One is VM and the other is VIN. For VM, if you're using a dual power supply, the voltage you can provide is 4.5 to 36 volts. For the controller's voltage, it's 4.5 volts to 9 volts. Why is it 9 or 10 volts? The reason is that this is the voltage that can be withstood by the node MCU's IC regulator, so it cannot exceed 9 volts. So what I want to tell you about this part is that if you are using a single power supply and you connect the short circuit ring, what is the voltage limit that you can use? Correct. It is determined by the controller voltage's highest value provided by the power supply, which in this case is 9 volts. Next, there are 2 control ports here. Why do we say 2 control ports? It's because of its pins. Motor A requires 2 pins to control it. Motor B also requires 2. Why is it 2 pins? I can explain it to you in the upcoming class. However, we can remember that motor A uses D1 and D3, all odd-numbered pins, while motor B uses D2 and D4 even-numbered pins, so it's quite sequential. You just have to remember that odd numbers are for A and even numbers are for B. It's similar to A and B sequential arrangement, so you can take notes on this. What does the motor control shield drive? It drives the motor. What are we going to use in the following class? Which motor? The TT motor. This TT motor also has its working current. What is its working current? It is not labeled, so by searching related information, we found that for a working voltage of 6 volts, its working current is 200 mA. If it is 3, then it's 150 mA. What does that mean? Suppose my power supply provides 6 volts. If my motor power supplies provide 6 volts, its current is 200 mA. Since we use a single power supply, how much power is provided? 8.4 volts. When Vm and Vin are used in parallel, which voltage do we use? It is two 18650 connected in series, so it's a maximum of 8.4 volts and a minimum of 7.4 volts. We can calculate proportionally. Suppose we use 8.4 volts to supply power, its maximum working current should not exceed 300 milliampere. Basically like that. However, this is without any load. When the motor is at a certain state, it will have a maximum current. What current is this? It is a maximum current needed to overcome the maximum static friction for the motor to rotate the instant it is activated. How much is it the maximum current? Normally, our estimate is 3 times the current without any load. So roughly using this method, assuming that our estimated power is 8.4, how much do we need? We will need about 3 ampere of no load current. If the maximum current at the activation moment is around 3 times, how much is it? 900 milliampere. What happens with 900 milliampere? It is within the power specs range of the motor control shield. So our choices are like this. When using both the motor control shield and the motor, we must consider whether the power specs are a match. This is the introduction to our hardware. What we are going to discuss next is how to control the motor and how it is driven. Next, we will talk about the wiring. Please pay attention and do the wiring as instructed. There is a motor A and a motor B. Motor A is connected to this part and motor B is connected here. One thing that you must definitely pay attention to is that when you are actuating the motor or when your motor control shield already has a motor connected, you definitely must have the battery powering it. Whenever you are using it, such as uploading data into the Node MCU, remember to set the motor control shield power switch to on. Why do we need to do this? If you don't do this, your power is off and you plug in your USB cable, who is supplying the power? The USB becomes the one supplying power, but the USB power capabilities are limited and is unstable for the whole system due to the Node MCU needing power and the motor also needing power, which will cause our Node MCU circuit board to become unstable and lead to write-in issues. So please pay attention. Whenever the motor is connected to the motor control shield, regardless of whether your program being written or not, since it's not possible to check, you must turn on the power of your power supply battery. Do not use the power push button on the Node MCU's motor control shield. In the beginning, we set it to an on state. When it's in the on state, do not touch it anymore. After the wiring is completed, we mentioned earlier that when we want to control any motor, we need 2 pins. We want motor A to connect to D1 and D3. Their corresponding functions are to control the rotation speed and to control the rotation direction. For our following exercise, let me remind you this. Suppose I want motor A to rotate forward, then I set D3 to high. If I want a negative rotation, I set D3 to low. If I want it to stop, I will set its rotation control value to 0. Explaining up to this point, you surely are intrigued with the question. When we were wiring the motor, it was never mentioned which wire is positive and which one is negative. Actually, it is like this. When controlling the motor's direction of rotation, in the beginning, we don't know how the motor will be fixed. If the left and right wheel use the same wiring method, the definition of positive and negative rotation will be different for the left and right wheel, and the direction will be different. So what do? Our most common way is temporarily connect the motor, and when the motor is fixed in position, then we write a program. Which are the 2 lines that we showed? We set the pin in charge of rotation direction to high. we usually say high for forward rotation. So at that time, if you connect to high and the pin is contrary to what you expected and is in the opposite direction, we don't modify the program. What do? We will adjust the motor's wiring and reverse the motor so that it gets the positive rotation that we were expecting. Before we start writing the program, let's review loop and setup that we talked about last time. In the beginning, the program we wrote was fairly simple. We only used loop. We only had an initial action that needed to be set up, so we used loop. As the program gets more and more complicated, there are some things that need to be done in the initial setup first. So we will bring out this program, building blocks. When using the program block, it will have a setup and includes the loop that we mentioned above. As we learn more complex programs, we would need to add this initial setup. So if the program needs it, we will bring out this program block. You can choose which one to use based on your needs. However, as the program becomes more complex, it is recommended that you get used to writing this program format. Let's practice the difference between these two programs. For the same program block, it would have different meanings when executing at loop or at setup. If executed at loop, as you see in this line, D1 is set to 1023, which means its power output is the highest. D3 set to high means positive rotation. We allow it to have a delay of 2 seconds. For these 2 seconds, it will perform a positive rotation. Next, we set up D1 to 0, which means stop. You must be curious about why the teacher did not set up direction, because stop has no direction, so we don't have to include it. Having the same program block placed below, their first time execution will be the same. However, if we place the same program block in setup, their execution results should be different. Next, we will hands-on test out the difference between these two programs. Let's go to desktop. Open the Arduino folder and click on Arduino IDE. We will be using ArduBlock. While waiting for the program, let's first check our wiring. Later during the operation, our wiring will be like this. We'll connect motor A. We don't download this for now. We'll connect motor A to this pin. Pay attention to this wiring. There is a hole nearby, which main purpose is to help you fix the wiring in place. When you finish organizing the wires, you can use a zip tie to tie them up. Pay attention to these 18650 battery boxes wires. This is particularly important because we added solder in here to make them thicker and make it easier to fix them onto the connector. But because it has a solder, it breaks easily. So during our design and when working with this, try to avoid any movement that can cause bending or warping of this part. You can set an angle for this wire so that once it's adjusted, it barely moves, and ensure that the wires don't break. Your wiring should look like this. Next, we can go into Arduino to operate it. Once you're in, select ArduBlock and enlarge the window. Let's bring in the pins. The first one is the digital pin setup. The analog pin setup and the order is like this. The analog pin setup is D1. For motor A, the analog pin setup is set to D1. We scroll down to the bottom, then D3. For the power output, we can write 1023. The maximum value is 1023. Then we place it in. After we place it, we need to have a delay of 2 seconds. For this delay, notice that the unit we are using is microseconds, and we'll set it to 2000 only. Once done, we'll pick the analog pin from the pin group to control its power. We can click on this again to put it away, then we can drag this and copy it. We move the unwanted parts back to the blocks area and set this to 0, which means stop. Then place this in. Once placed, we need to upload this. In the same way, we move the Arduino IDE to the side. We can look at it while operating. We don't need to update this. Let's take a look at our wiring. Remember that before plugging in our USB cable, we need to do one thing. When the USB needs to be plugged onto the Node MCU, we need to turn on the power. The power switch is located here. As you can see, it shows on and off. So we switch this to on. And the board will light up. If you turn the power on but the light is not on, the reason may be that this power push button was touched. In principle, avoid touching these and use the one on the side because you can see the state display. This way is clearer. Next, we plug in the USB cable. When plugging the USB, I often see students shaking the USB side by side to unplug it. Don't do this because this small USB head is actually quite fragile. After shaking it a couple of times, it may get broken. Next, let's take a look down here. After finishing with the wiring, check whether our board is correct. And also check if the serial port is connected correctly. We can choose COM3. You can look at the bottom, there's an indication here. At the bottom of IDE, it will show which board it is and where it is connected to. Once we're finished, we'll upload it. To upload, the first thing you'll be asked to do is to save the file. The file format is arduinos.ini file and it's not rdublock. So if you want to use this program later, you can save this file directly. An error has occurred. Why is there an error? There are several reasons. Last time I told you that the first one is whether the wiring is correct. We just checked that the wiring was done correctly. The second reason is whether our COM port was chosen correctly. Let's take a look here. There's a COM1 and COM3. So have we chosen the right one? We checked that we chose the right board. And the serial port is also correct. If we are still curious about the serial port setting, we can click on the Device Manager. Open the Device Manager to see more detailed information. We click on Device Manager and check in here. There is a port. Inside port there is a COM3. You can see that COM3 is not our original connector, because if we connect to it, it should show CP2102. So what we can do now is to unplug our USB cable and plug it back in. Then we confirm whether the connection is normal. The previous connection was probably abnormal. Therefore, if you see COM3 or COM4, don't think that because it says so, then it's probably our port. This is incorrect. It's not certain. Sometimes we need to open the Device Manager to check. So it's clearer. In the Device Manager, we can see that it's COM4. So we go back here, we click on Tools, and have a look. It is at COM4. We choose the port again. We check whether at the bottom of the IDE, COM4 is shown. Then we upload it again. Once we have uploaded it, you will see that the motor is running and it doesn't stop. It will rotate constantly. This is the structure of our program. It will constantly run the motor. Let's make a modification. We will add in the original loop. We'll bring out program. I will also show an incorrect action for you to see. Suppose I place it here, then I place program here. And I also add in loop. When uploading, it will tell you how many loops were found. Why? Because there can only be one loop within the program. When two are present at the same time, it won't know which one to execute. So remember that this should be put back into the blocks section. Then we upload it again. We can take a look. When uploading, this light will turn on, which means that the program is being uploaded or downloaded. We take a look. When the upload or download is completed, it will execute and then stop. Suppose that you want to repeat the execution, there's a button here called RST to repeat the activation. To repeat the program execution, press again the reset button. What is the purpose of this function? It will run the whole system again. This means system reboot. Starting over from setup, it rotated a bit and stopped again. Press reset again, it ran for 2 seconds and then stopped. According to this program, you probably know the difference between setup and loop. Setup will only execute once and stop. If it's a loop, then it will execute continuously. Okay, you can practice and operate yourselves. After the operation, let's take a look at this. As I have already told you before, there's a RST button next to the node MCU's USB. This RST represents the reset button, so if you need to reset the whole system and execute again, you can reboot using this reset button. Hello everyone, we are going to talk about how to control the motor's direction of rotation and speed. First of all, we will briefly review the principle of a motor. The components of a DC motor can be divided into 3 parts. The first part is the stator, which is composed of magnets. It will create a fixed magnetic field. The second part is the rotor, which is the rotating part. It is composed of a copper coil. When the current flows through, it will generate a magnetic field inside the copper coil. Once the magnetic field is generated, it will create an attraction or repulsion effect with the stator's magnetic field. This motor will begin doing what we call rotation. When the motor starts to rotate, in order to continue supplying power to the copper coil normally, there will be a carbon brush and commutator to provide current. So a motor can be divided into these 3 parts. Who determines the motor's direction of rotation? It will be determined by the current of the copper coil. When we supply power to the motor, if we switch the positive and negative terminals, the direction of the current flow will be reversed. And the generated magnetic field will also be reversed, so the direction of its rotation will be opposite. If you want to control the motor's direction of rotation, You can do it by changing the direction of the current to achieve this. Let's move on. For the motor control shield used to control the motor, we often see a type of circuit called the H-bridge. Let's take a look at this. Before we talk about the H-bridge, let me explain the basic concept. First, we need to control the motor's direction of rotation. How do we start it? We need to install a switch. This switch is in charge of turning on the motor. Second, the current direction controls the motor's direction of rotation. If starts from the positive terminal, our current is positive and the motor will also be positive. Positive connected to positive, then the motor has positive rotation. If the power supply of my motor is opposite to its polarity, the rotation of the motor is going to be opposite. So we use the inverse polarity of the power to change the motor's direction of rotation, which is related to the magnetic field and current needed to rotate the motor, as explained previously. Okay, let's move on. If this circuit can only control one direction, then it's quite inconvenient. So we are going to use this kind of circuit called H-bridge. Why is it called H-bridge? Because it is in the shape of an H. That's why we call it H-bridge. For the control of the direction, suppose we want a positive rotation, what should the working direction be? Let's move on. We just need to turn on the A switch and D switch. When they close, the current will flow this way. The current comes from the positive terminal and flows through the motor. Then goes to ground. This way, it's positive rotation. If it's the other way around, if I turn on switch C and switch B, the current will flow from the negative pole. Since this is positive, the current flows from the negative pole to positive, then ground. The motor will have a negative rotation. By using this method of controlling the motor's current's positive and negative poles, we can control its direction. Let's take a look at this transistor. Why do we need to use a transistor? Because in an IC, our H-bridge will turn the IC into an integrated circuit. We can't put a switch in it, so we need to use a transistor to replace this switch. Let's take a look at this transistor. When you are trying to understand the transistor, we will look at it as if it were a faucet. We can see this base current as the faucet's handle. We'll see the outlet of the faucet as emitter current. There is a base current which works like a switch. So what we see here is called an Npn transistor. How do I turn this transistor into a switch and make it work? We can understand it like this. This is an arrow, which is a symbol that represents current flow. I'll give it a positive voltage. Then we connect this. If it's positive here and negative here, this will be in a conducting state. Current will flow through this transistor. Another kind of transistor is called Pnp transistor. Likewise, we can look at the direction of the arrow. If the base charge is negative, and it's negative over here, then this will be in a conducting state, and the current will flow. Its principle is like this. We will look at the direction of the arrow. As long as the direction of the arrow is the same as the polarity, we can determine whether this transistor is in a conducting state. Let's take a look at this H-bridge. We've already replaced the switch with a transistor. Let's take a look at this circuit. Suppose that in this state, I give input A a 0, which is a low electric potential. Then I'll input 1 in here. I will input a high electric potential. We will label it high electric potential here and low electric potential here. When it is like this, we can determine that it's positive here and negative here, and it's 1 here and 0 here. This is in a conducting state, so this is on. Let's take a look at here. This is low, and this is ground. Low to low, so what happens here? It's non-conducting. Then let's look at Q3. Q3 is positive. It's high here, which is also positive, so what is this? High to high, it's non-conducting. It's positive here and ground here, so the current is on state. This loop will form. Q1 to Q4 is conducting. So the current will flow into the motor from the positive terminal and flow out of the negative terminal, and the motor will start to rotate. This will generate a positive rotation. Let's move on. If it is the other way around, this time it's 1 here and 0 here. What will happen? Let's take a look. This is positive, it's 1 here, which is high, so it's also positive. So what happens with this circuit? Q1 is non-conducting. Let's look at Q2. Q2 is high and it's ground here, which is low. Therefore, positive to negative, so it is conducting. Q2 is conducting. Let's look at Q3. Q3 is positive and the input is negative, so it's positive to negative, so it's conducting. Then Q4 is 0. It has low electric potential. This is also ground, so 0 to here is non-conducting. According to this assertion, you know that the direction of the current is from the positive terminal flowing into the motor's negative terminal and leaves from the motor's positive terminal, and the direction of the motor will be reversed. This way, we will have a reversed motor. Next, let's have a look at this. With this, we can summarize the following table, which will tell us if we want the motor to have a negative rotation. Our input and output should be like this. If we want a positive rotation, input A and input B should be in this state. From this, we can see that there is this following property. If input A and input B have the same polarity, the motor will not rotate. They must have opposite polarity for it to rotate. Let's move on. We talked about how to control the motor's direction of rotation. Next, how do we control its speed? Who decides the speed of the motor? The speed of the motor is determined by the voltage you give. As you can see here, suppose it's 0 volt here and 5 volts over here. As our voltage keeps increasing, my rotational speed starts from 0 to here. Let's say it's 200. This RPM means revolutions per minute. The higher our voltage is, the higher our rotational speed will be. We can say that the motor's rotational speed is proportional to its voltage. So if you want a faster rotation, increase the voltage. How can we achieve this within the circuit? We can look at this. We will use the H-bridge that we talked about. We will add a combinational circuit before it. This is a logic gate, which will not go into detail. What I will say about this is that for the control of the direction of rotation, we will make use of this logic gate to merge two of the pins together, this pin with this pin. These two pins that I've marked with a cross, they originally determined the polarity, and through these combinational logic circuit to assemble them together, we'll use one pin to control it. In here, I'll add another pin, which I can send the power signal to it. I'll name this Pwm. Why call it Pwm? I'll explain later. We can use a H-bridge on our motor to determine its polarity when controlling it, which can determine its direction. We'll use another method for speed. Previously, we said that we could use the voltage magnitude to change the motor's rotational speed. How do we change the voltage? Let's take a look. How to do a PWM? Let's take a look at this. Our node MCU is a digital control system. its voltage can only vary between 3.3 or 0 volt. But what do we want? We want a voltage that can be high and low, just like an analog circuit, but it's not possible. We cannot make any changes in the y-axis. In the digital system, the y-axis doesn't change because the digital system only has high and low states. Let's change our perspective. We make changes to the y-axis. How do we make changes? Let's take a look at this. The method that we'll use is like this. Within a fixed cycle, I want one section of it to be conducting, while another section of it to be non-conducting. Overall speaking, if initially our output is a waveform of 3.3 volts, if this section is 1/3 of the waveform and this is 2/3, I can see that I only provide 2.2 volts here. Let's combine them together. Comparing to this, you will be able to understand the following. Within a duty cycle, part of it is conducting and part of it is non-conducting. We'll use this way to control its voltage magnitude. We call this method pulse width modulation. Let's look at it this way to be clearer. Suppose I wanted to have a full power output, then we fill in every section. If I only want it at half power instead of a full power output, within my fixed cycle, I only have half of it in a conducting state. I only need half of the cycle to be in a conducting state. As a result, our output voltage will only be half. What will happen to its speed? The speed will probably be halved. We use this pulse width modulation technique to control it. We can simplify it and call it the Pwm Control Method. For the motor's direction and speed control, we can achieve it this way. As explained to you earlier, we will give it 2 pins. One pin is in charge of speed and one is in charge of its directionality. We can set the speed between 0 to 1023. The higher the voltage, the faster the speed. The lower the voltage, the slower its speed. For the direction, we will use D3 and D4. Different pins for different motors, using high and low to control its direction. Since you have previously practiced writing a program, we will ask you to try and write this yourselves. Let's practice. We want our motor to rotate forward at full speed for 2 seconds, stop for 2 seconds, then rotate backwards at half speed for 2 seconds, and then stop moving. Try to figure out how to write this program. Let's take a look at this program. If you have finished writing this program, let's take a look. The program should be written this way. The first thing I would like to remind you is that the whole command should be written in setup. Why? Because we have a condition, which is to stop moving. What does it mean? These actions are executed once. Once they have been executed, it will not be repeated. If we don't want to repeat them, we must place all these commands inside setup and not inside loop. Is there anyone who can check for me? Which of these commands is redundant? Which line can be removed? The line that can be removed is this one. Once we execute the stop command, for example, we want to stop here. If we want to perform a stop action, its direction is meaningless. Why? Because it has already stopped, so there is no need to write direction. We can remove these two lines. If we want to restart our motor to rotate again, what do? I mentioned this to you before. Let's take a look at this. I have already written a program and uploaded it. Let's have a look. I have already uploaded the program. I'll have my finger press it down in case it jumps up. There is a RST here. We press RST once. The motor will rotate again. Positive rotation. Just like this. Practice a bit, because for our upcoming actions, we will be operating this motor, so you need to familiarize with it. Let me remind you again that if we want to operate the motor, whenever the motor is connected to the motor control shield, no matter whether we make it move or not, remember that our power supply, in other words, our battery box's power switch, must be in the on state to ensure that our power is not supplied by the computer. The second thing is that whenever we want to operate this car, we have to ensure that the batteries are charged, because if you over-discharge the 18650, the batteries will be damaged. For every class, we need to maintain the habit of measuring if the 18650's batteries have electricity when you come to class. Let's operate this once for you to see. We'll check if the 18650 battery is charged. Let's take out our multimeter and switch its setting to the DC voltage 20 volts position. The place where we will measure is here, the positive and negative terminals. Red to red, black to black. When connecting, check if the probes have been inserted in the wrong place, because you never know if the student before you paid attention to this. The common connection is black, and we want to measure voltage, so the red probe is connected to here, and then put it in. Don't short circuit the pins. Like this. We'll hold it with our hands. The battery voltage is 7.47 volts. One battery is 3.7 volts, 7.47 for two. It is almost reaching the battery's low limit, so you need to pay attention to this and let the teacher know that you need to recharge the batteries. So you must pay attention if you need to use the batteries. You must pay attention to their voltage. The 18650 may get damaged when over-discharged, so please pay close attention to this part. We've talked plenty about motor control. Next, we will review the input part that we talked about earlier. We will use the infrared sensor to control the motor's movement. Just like our previous exercises, what we're going to do now is to use the infrared sensor as a switch. Let's see how we do this. Let's take a look at this diagram. The reading from the infrared sensor will be sent to the node MCU. Then the node MCU will determine when your finger moves over. Whether you are contact or not, you will receive two different signals and make an assertion from that, and then actuate the motor. That's the action we do. First, we need to reconnect the wires. Do you remember what you need to do when doing the wiring? Whenever we are doing the wiring, please beware and turn off the power. Make sure you have this habit. Let's have a look. First, remove the USB cable. Remember to turn off the power. Let's move on. Take out the infrared sensor. For our pins, we will connect the positive and negative terminals first. Notice the place where the VCC and GND are connected. VCC is connected at the middle row, which is positive. Also, look at the connectors above and check if any of them has any problems. That is, these thick copper pins must not short circuit with the adjacent ones, because this will cause problems to this control board. Let's look at DO, which is the analog output. We will connect it to D6. Correction, DO is digital output. We will connect it to D6. We'll connect DO to D6. Next, we connect AO to AD. It's not A0, remember to connect to AD. Like this. We can then use this circuit to perform the next action. Next, we're going to connect the USB. Remember that the power must be turned on first. Turn it on and the light will be on. The last program will be kept. It doesn't matter, we'll let it execute. After it's done, we'll plug in our USB cable. We can perform the next step. Let's take a look at this flowchart. We will obtain a reading from the infrared sensor and we will use this reading to determine whether it's true or false. If it's true, we will actuate the motor. If it's false, we let the motor to be turned off. For the overall process, we will write a program. If you are familiar with each component and program, and you don't have any problems with the basic explanations, we can go over more steps at once. If you're still quite unfamiliar, we recommend that you do it step by step. First of all, let's check the infrared sensor's readings. We read it in first. Okay, let's have a look. We have to open Arduino block. And read in the value. We can remove our previous program. What we are going to do now is to read in the data from the D6 pin. We go to pin, then digital signal. Oops, we grabbed the wrong one. We need to grab the digital pin block. Then we need to find an adapter and add it on. Let's upload it. After the upload is completed, we can perform a check because we just connected a cable. When connecting it, we don't know if there is any problem with the connection or whether this board is working fine. So we can use the software to perform a checkup. Using the software to check if the cable has any errors. Once it's done, let's look at the serial monitor. When we approach our finger to the sensor, it will read 0. When we remove it, then it would read 1. We've confirmed that the data is definitely being sent to our database. Next, we will move forward to the next step. Our data was definitely received by the node MCU. Next, as mentioned to you earlier, when we are starting with a new program, start from the things that you know. Do not attempt to do many things at once. When the data is sent in, let's not control the motor yet, because we are more familiar with the control of the LED. So next we will perform control of the LED first. Up to here, we need to add an if-else statement. Our LED is the D4 pin. We bring out the digital pin setup block. For our evaluation, we will copy from the D6 digital pin. We'll evaluate from this. We need to select the D4 pin. If you're connected to it, what kind of action do we want it to perform? We'll copy this. D4. Here comes the problem. If our hand contacts D6, it will be 0. If so, then it's false. If it's false, then the else section will be executed. If it is true, it will execute the then execute section. If it is false, we will execute the otherwise execute section. When we approach our hand, the LED should light up because the LED light on this board performs a low state action, so we need to change this to low. Let's upload it. When uploading, we can see this light blinking. When it stops blinking, it means that the upload is complete. Then we can check if the program written is working as we expected. Let's hold down the infrared sensor using our finger. At this time it is 0, so the LED lights up, so our program is working correctly. Also, let me tell you that when looking at here, there are 2 LED lights blinking. When there is an obstacle present or not, it will affect this one, which turns on and off. There's another light that is always on. What light is this? This is the chip's power light. Whenever it is powered, this light will be turned on. Just to let you know about this, when this is done, we can move on to the writing of the next program. We can already control this board. What we'll see next, the LED is done. We can control the LED. What is next? Replace it with the motor. Let's try doing this part. Let's put aside the LED blocks parts. Let's recall which pins are needed for the motor. We have motor A connected right now, so we need 2 pins, which are the digital pin setup and analog pin. We can take them out first. The analog pin is D1. For motor A, D3 is in charge of it. So we choose D1 and D3, and we let it rotate. We type in 1023. There is a question now. Do we have to do it like before and approach the hand to activate it? We should place the motion part in false, because for our infrared sensor, it is false when touched. So we place it in the otherwise execute section. Then we copy this. When our finger is removed, it will be true, and it will send back a 1. So here we will input 0 and press enter. Let's upload this. It is suggested that when you are working with this, if you are not familiar with this system, we recommend that you do it step by step, starting from the confirmation part, then move on to the next step when each step is correct. Why should we do it this way? There's a very important reason. When the system is very complex, it requires more experience to perform debugging. When you're not as experienced, we recommend building up each structure step by step. This way is safer. When the upload is completed, let's have a look. In the same way, use a finger to touch the infrared sensor, the motor should activate. When the finger is removed from the infrared sensor, the motor will stop. Our program is working correctly. We'll do a demonstration. Let's take the infrared sensor, approach our finger, and the motor will activate. When our finger is removed, the signal received is 1, and the motor will stop, which means our program is working fine and is written correctly. Remember to go step by step, then we move on after it's correct. After we check that the motor is running correctly, we'll move on to the next step. You can try it out yourselves. What we are going to do next is the most important part of today's class, how to do feedback control. I remember that in the beginning I told you that if we want to control the motor's speed, we set a rotational speed and hope that when the motor is rotating, it will go according to the speed set. We have to break this problem into two sections, because if I ask you to do the speed control at once from the beginning, it is actually quite difficult. So we will divide this problem. How shall we divide it? First, we will measure the motor's rotational speed. Once we understand how to measure the motor's speed, then we will try to control the motor's rotational speed. Let's have a look at the following. How do we measure the motor speed? Let's have a look. What we are going to use is the infrared sensor that we are familiar with. Let's have a look. We are going to start by measuring the motor speed. First, let's take a brief look at the wiring that we will be doing later. For the wiring, we have already taken an infrared sensor and connected it to D6, which will be used as a switch. Next, we need to add a new sensor. It is also an infrared sensor, which will be used to measure the motor speed. We will connect it to the D5 pin. What is the job of this infrared sensor? Its job is to measure the motor speed. For the motor speed, let's look at the following picture. We will install the motor onto a wheel. When installing it to the wheel, beware not to install it too tightly. Why? Because between the motor and the wheel shaft, they have a tight fit. What does tight fit mean? It means it's very tight, so once installed, it will be hard to take it off. Sometimes if we take it off, the motor shaft may get pulled out altogether and break. Please bear in mind that when installing it, don't do it too tightly. If in any case, you really pull the shaft out by accident, what should you do? It doesn't matter. Our motor has a dual shaft output. You turn it over and you can still use it, but try to avoid this situation from happening. Let's take a look at this. We'll install the motor onto the wheel. Then we do the wiring. When doing the wiring, let me remind you that you must cut off the power. You have to develop this habit instead of thinking it would just take a second. Yes, it takes 1 second to burn it. You have to develop a good habit when doing the wiring. You must turn off the power. We can also try doing the wiring as shown in the picture. When you are done installing the wires, let's have a look. On our motor, and wheel, as you can see, we need to put a white masking tape. The reason for the white masking tape is it has better reflectivity, so for the case that there is no white masking tape available, you should choose one with a better reflectivity. Once done, we have to measure the white tape turning one full circle. When the white section comes back, it means it did one full rotation. When it senses the white section, check the light on top. The left one lights up. There are two sets of lights, left and right. When I distance it, the light will turn off. It definitely sensed the white section. When I move it to the black section, it shows no response. It does with white, but not black. This is the normal sensing action that we need to perform. If your light doesn't turn on, both lights are off, it means that there is a problem with the sensor. If this light is on but this one doesn't, no matter what you do, what should you do? You can change this variable resistor. You change it to this one used for calibration. What are we calibrating? So that when encountering black and white, it will work normally. This variable resistor is used whenever we encounter a new environment or a new object and need to adjust the ratio. Calibrate to what extent for it to react. How black it has to be to get a response. All this is adjusted through this variable resistor. After checking our infrared sensor to ensure that it will work well for later. How do we measure the speed? First, we need to understand the concept of rotational speed. What is rotational speed? It is the amount of rotations done around an axis within a fixed amount of time. The unit we commonly use is RPM. Revolutions per minute. Whenever I say RPM, what does it mean? How many revolutions it can do in 1 minute? This is what is commonly used. How do we measure the rotational speed? Let's look at the steps I wrote. Step 1. When the infrared sensor detects the transition from black to white, you record the time. After 1 revolution, when it transitions from black to white a second time, it means it's turned to a second revolution. So you record this time. What does the first and second time difference mean? It is the time it took to complete 1 revolution. We record the time for these 2 identical situations and calculate the time difference, which means the time it takes for 1 revolution. We need to calculate RPM. There is a timer function in the Node MCU called mils, whose unit is in microseconds. So these 2 times calculated are in microseconds. So in order to convert it to RPM, we use this function at step 5. 1 minute divided by revolutions divided by microseconds. The function is rearranged to 60 times 1,000 microseconds, then divided by the time difference. This way you can calculate RPM. You can think of how this program should be written. Let's take a look at this flowchart. The flowchart is written this way. First, we wanted to have a switch. If the switch is not turned on, then the motor will not activate and the measurement cannot be performed. Let's move on to the next step. Let's say that our switch is turned on. We are in the true condition. Let's look at this next. When our finger approaches the infrared sensor responsible for the switch, we will trigger the motor to start rotating. The infrared sensor is in charge of measuring the speed, will also start working, and it will assert its status. As I said earlier, we want our state to be black, and then transition to white. Our wheel should be like this. It is in the white status. Whenever it transitions from black to white, a time is recorded. We need to perform this action. The time recording is only done at this moment. When starting the second lap, we record the time again. What is the first time recording for? We take it as an old time. When the second lap comes in, it will be a new time. By using these 2 times, I can calculate their time difference. Using this time difference, we are going to control the speed. The calculation of the time is all done inside the true part of this if statement. This part is for you to understand. For each status detection from the infrared sensor, we continuously perform analysis. For each assertion performed, the current status becomes the old one. We need to perform this outside this if loop. Once finished, we go back to here. It will ask again whether to continue with the measurement and keep going. This is more or less the process. Let's take a look at this program code. The program code looks like this. Let me briefly explain it to you. The first thing is the setup of the rotational speed. We use a constant to set the speed. We use an integer as a time variable. The second thing is our switch. We'll use D5 as a switch. This switch will determine whether we want to perform measurement or the motor to activate. If it's true, which is when my finger distances, this portion performs a stopping action and we turn off the light. If it is false, which is when my finger approaches it, the infrared sensor obtains a false reading. What does it do? This action is to begin with measurements. The wheel of the vehicle will start moving. What we are going to do next is the variable declaration. What is this line for? This is an integer type variable. Why is it called integer type? You can think of it this way. Our sensor can only do 0 and 1. It is actually a Boolean type variable which only has 0 and 1. So we can use an integer type to declare it. The first time this is written into the if statement, a value is written in. We can look at here. It's this one. The reading written in from the outside is new. A new reading is written in, which is the current value. If it is a low electric potential, what does it mean? That it is white. It will compare to the previous status. If the previous status is high, it means it's black. What does it mean? It has transitioned from black to white. At this moment, we will try to calculate a time difference. The first time with this status, we obtain a millis. What millis means is the time obtained at this moment. If we already have an old time, then the rotational speed can be calculated, which will be done in this line. If it is the first recording, then this line has no meaning. Once it goes a second lap, the old data is brought in to do the calculation, and then we can print out the calculated rotational speed. Once this action is done, if you're done with the time difference, then this has no other use. We can use the millis obtained and turn it into the old time, and wait until the next time the wheel transitions from black to white. Then we use it to calculate the time difference and solve for its rotational speed. In the last section, we will take the detected status and set it as the old status. This is the whole process. You can give it a try and write this program code. Let's have a look. After we uploaded the program, we can operate this together. We'll use D5 as a switch and D6 as the sensor. When we approach our hand to the infrared sensor, we will see that the motor next to it will obtain a speed. See? From the serial monitor on the right, we can see its speed. When I remove my hand, it will stop. This is a simple speed controller. Let's take a look at this program. What we are going to do next is this. When you're finished writing the program, let's have a look. After we executed it, you all saw the results. After you finish with the program, you will realize by looking at this program that writing it is actually quite complex. We're going to introduce another concept. As your program becomes longer, you definitely need to use this concept called a subprogram. It has two advantages. The first one is that it simplifies the layout. This way the layout doesn't look too complicated. Also, it gets a bit easier when you read your program code. It improves the overall readability, and you can go over the code faster. The second advantage is its usability. Some commands can be reused, which can be done by means of subprogram. Next, let's take a look at how we can write our subprogram. Let's go back to our original program code. The subprogram command that we will use later is inside this blocks area. We can choose subprogram, then select correspond. Then we copy it. What we are going to do later is divide it into 3 subprograms so that the programs look simpler and not cluttered. The first subprogram we are going to make is stop. S-T-O-P. For correspond, we also type stop in capital letters, then press enter. Then we will drag this program over and then place the stop block in. Looking at these 2 commands, you may need to think about it, but when you see stop, you don't need to think about it, and know that this command is for stopping. Its readability is better. The second subprogram I want is move, M-O-V-E. We'll place it in the correspond block. We want to make the wheels move, M-O-V-E, press enter. The following line and all this section below is for detection, is the test part. So I will name this test, T-E-S-T, then name the corresponding block test as well. Then we place this corresponding block under move. Put this back. Now you would think that this program code looks more refreshing. We'll adjust it a bit. The overall program should look a little more refreshing, with better readability, and it will not look so chaotic. Let's take a look here. If we use subprograms to organize our program code, you'll probably think it's more refreshing and it's easier to look at. It's more intuitive. There are no issues with stop and move, and there is no need to pay attention to these commands. If we have problems with test, we can go over this section to discuss and think about it in detail. This way is easier to do. Okay, so now that you know how to use subprograms, you can organize your program code. What we are going to do next is our feedback control's last theme. After organizing your code, you have also uploaded the program and tested that this program works correctly. Next, let's take a look at the rotational speed control. When controlling the rotational speed, we've already finished with the speed measurement. What we are going to do next is this. We will send back to the controller the value measured by the sensor. In our control system, we call this a closed loop circuit. It will send data back. And then after it is sent back, the controller will compare it with the initial variable requirement input. Let's say I want a constant speed of 500 RPM. Suppose our constant speed requirement is 500 RPM, our sensor measures a rotational speed of 300. What does this mean? The controller's speed needs to be increased. To increase this, our output power needs to be adjusted up. If we ask for 500 RPM but it's already 600, then our power output value needs to be adjusted down. This way, we send back the output's physical quantity so that the controller can perform adjustments. This is called closed loop circuit. Just now, once we finished with the speed measurement, It is time to do the motor's variable speed. There's no need to change the wiring. What we need to make adjustments is in the input. We are going to set up a value for it. What we are going to add is this. Let's look at the algorithm. For the writing, we have added certain parts. But the overall structure of the program more or less looks like this. Let's take a look. First of all, we have to give it a setup. We need to define the target speed to be achieved. Here we will give it a target speed. We will also give the motor a starting speed. We will provide these two things because we will reach the expected target speed through the correction of the motor's rotational speed. The next step is the same as last. Do we want the motor to activate? If it's false, then the motor will not move. If it's true, then the motor will start moving. When it moves, we'll use the default power value to do the rotation. Let's look at the following. We'll start to evaluate, just like before. The key aspects are the same, except for this most important line in the program code. What does this line mean? If we want to modify the motor's setup value for the desired rotational speed, for the case the rotational speed is too fast, how can we adjust this setup value so that the speed is slower? Who decides how slow it should be? It's decided by this, the difference between the actual speed and target speed. Let's give an example. Suppose that our rotational speed is expected to be 500 RPM. The measured speed is 300. This is our target speed. And this is our actual speed. What does it mean? What should my PWMP speed be? I need to increase it. I need to add a value to my Pwmp. The way we do this is by subtraction. We subtract the actual speed with target speed, 300 minus 500. What's the result? It will be negative. Therefore, this value should be increased. Using this value difference method, if the speed is too low, we'll increase the value of its power output. If the value difference is positive, what does it mean? The speed is too fast, so what do? We reduce the speed. The key lies in this line that we newly added. Let's take a look at our program code. Right here, we've already been through the concept of subprograms. So it will be more refreshing when writing this. The stop section is not changed. The move section also remains unchanged. We just need to add this line. What is this line for? This line will do the value difference calculation. What will this value difference be used for? Its most important function is to adjust the PWMP. I want to adjust here. After I calculate the value difference, I will set it as a new power value. If the speed is too low, then I will replace the value of this Pwmp, and this number will increase. As this number goes up, the motor will rotate faster. You can try it yourselves. Once you're finished writing, you can do a test run to see if it's completed as expected. Once you're finished writing your program, let's have a look. Our target speed is at 188 RPM. When we start, we set the motor's power value. We set up how much power to give. We'll give it 1000. After we upload it, let's take a look at the monitor. Then we'll activate it, and it will start to run. You can see that RPM is our current speed. Our target is 188, so you can see that the speed is lowering. Afterwards, it will stop and maintain the speed at 188, 187, 189. we can definitely complete our target speed control. We can also practice to see if there are any problems. You can also discuss with your classmates. Hello everyone. The course we are having today is the servo, which is also called a servo motor. Let's take a look at the internal structure of the servo. It can be divided into 4 parts. The first part is the motor. The motor has a high speed, low torque power output, but we want a higher torque, so we will reduce its speed and increase its torque using a set of gears. During the rotation process, it also has a variable resistor, which will have the same angle of rotation as the servo. So the angle of rotation will change the variable resistor's readings. This reading will then feed back to the controller, and it can sense the servo's angle of rotation, whether it is the same as the expected target angle. If it's not, it will move towards the direction of correction. It can also feed back to the controller system. In the beginning, let's look at what we talked about in our previous session. For our input, we set a target angle value, and then the controller will rotate according to this angle. The angle rotated will be feedbacked to the sensor. This sensor is the variable resistor. It will feed back to the controller the reading and tell if the angle is right. If it's not, then it needs to increase the angle. If it's exceeded, then the angle needs to be reduced. This is the servo's job. Then let's take a look at the following. The servo control is quite special. It uses pulse width modulation. This is not for the modulation of power output, but it uses pulse width modulation to notify the controller the angle it wishes to rotate. It uses Pwm to do so. Each cycle is 22 milliseconds, so if my width is 0.2 milliseconds, it means that the servo turns 0.5 degrees and so on. Suppose it needs to turn a 90-degree angle. An input cycle will be given with a working cycle pulse of 1.5 milliseconds. The servo will turn the desired angle based on this method. In general, servos range between 0 to 180 degrees. However, certain special servos can turn 360 degrees. I'll explain about it when we encounter it in upcoming classes. In principle, the pulse width is between 0.5 and 2.5 milliseconds, but this may not always be true. There will be specialized settings for specific servo angles in Arduino block. When you operate later, if you can clearly know the model of your servo, then we can choose an adequate working pulse width signal to modulate. Let's first practice this. We should have an SG90 in hand. Let's take a look at this operation. Let's go back to our Arduino block. We click in. Once inside, we'll make a simple loop. We click on Generic Hardware. We go in and grab the servo block. For the servo, we try to select the D6 pin, and the angle of rotation we input is 90 degrees. There is a servo default here, and you can select SG90. If you have an MG996, you can choose this one instead. The one we have is SG90. The rotation angle is up to 90 degrees, and you don't know if this angle is achievable, so we will have 2 of them, just like our blinking circuit. We'll give it an angle value. It doesn't need to be big. We'll give it 120 degrees. And make it go back and forth between 90 and 120. We don't want it to rotate repeatedly, so we use the setup section in the program block. This way it won't rotate repeatedly. Is this correct? Is it alright to write it like this? Of course not. Why? Because the rotation is very fast, so we won't be able to measure whether the rotational angle has been completed. Remember to add a delay. Use a 2-second delay on this 90-degree angle. 2000 milliseconds, then we upload it. If the upload is complete, this light will stop blinking. We'll let the program upload. If the upload is completed, and it has completed its execution, if we want to repeat it, we press the reset button, and it will execute again. Let me ask you a question. Is the servo considered a motor? The answer is yes, because it only differs in the addition of a controller to control its angle. Therefore, if you want to operate a servo, do we need to turn on the power supply? Yes, we do. Beware not to power it with a USB, because its power capacity is limited, so we still need to use the battery for power. This way the power system is more complete and more stable. You must pay attention to one thing when operating a servo. Suppose I want the servo to turn 120 degrees, but it gets stuck at 90 and cannot turn past it. What will happen with the servo? It will burn down. Why will it burn down? Because when it can turn to that angle, the motor will start increasing its current. However, it gets stuck. This is called stalling. The rotor gets blocked. When the rotor gets stalled, the coil is equivalent to short circuit, so the current becomes infinitely large. When the current gets infinitely large, the current will continuously increase, and the motor will overheat and then burn out, so you need to be careful with this. When working with the servo, if the rotation angle gets stuck, it may burn down. Therefore, you must be careful when working with the servo.